Hello everyone and welcome to this session on 8086 minimum and maximum mode of operation. This session is a part of the module 1 of the course CS305 microprocessors and microcontrollers for the 5th semester BTech Computer Science and Engineering students under the APJ Abdul Kalam Technological University. Myself Anu Maria Joykutti, Assistant Professor, Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. First, let's see an overview of the 8086 microprocessor. The 8086 microprocessor is a 16-bit CPU and it is available in 3 clock rates for the various versions, which are the 5, 8 and 10 MHz. It is packaged in a 40-pin dual inline package and it has got 2 operating configurations. The 2 operating configurations are single processor or the minimum configuration mode and multiprocessor or the maximum configuration mode. Now let's look in detail about the minimum mode operation of 8086. The 8086 microprocessor will operate in its minimum mode by strapping its MN MX bar pin to a logic 1. That is, whenever this pin, the MN MX bar pin, is set to a logic 1, it will be the minimum mode configuration or a single processor mode. Here all the control signals are given out by the processor itself. There will only be a single processor in the minimum mode system. And all the other remaining components in the system includes the latches, the transceivers, clock generator, memory and I/O devices. The latches are generally the buffered output D-type flip-flops. These latches are used for separating the valid address from the multiplex address bar data signals, that is from AD15 to AD0, and these latches are controlled by the ALE signal, that is the address latch enabled signal. Now the transceivers that is there in the minimum mode are the bidirectional buffers and they are also known as the data amplifiers. These transceivers are used to separate the valid data from the time multiplex address bar data signals, that is from AD15 to AD0. In order to separate the valid data from the AD15 to AD0 signals, we require these transceivers. These transceivers are controlled by 2 signals, namely the DEN bar and the DTR bar. The DEN bar is the data enable signal and the DTR bar is the data transmit and receive signal. The DEN bar signal indicates whether there is a valid data that is available on the data bus, and the DTR bar signal indicates the direction of the data, that is whether it is a transmit operation or a receive operation that is being happening. The timing diagram for the minimum mode of 8086. Now, we can understand the minimum mode working better if we look into its timing diagram. So let's see the timing diagram of the 8086 minimum mode operation. Here in the minimum mode, the opcode fetch and the read cycles are similar, and hence the timing diagram can be categorized into 2 parts, or it can be divided into 2 parts, which are the timing diagram for the read cycle and the timing diagram for the write cycle. Now let's look into the read cycle timing diagram for the minimum mode operation of 8086 in detail. As we can see from the figure, the read cycle of 8086 consists of 4 clock pulses from T1, T2, T3 to T4 and 1 intermediate wait cycle of TW. Now, this complete cycle of clock pulses from T1 to T4 and the intermediate TW state make up 1 read cycle of 8086. Alright, so in order now, the read cycle for 8086 begins at T1 with the assertion of address latch enable and the M bar IO signals. That is, in order for any read operation to happen, there should be a valid address that is available. That is the address that will indicate from which location or from which device the read has to be performed. Okay, so this is being indicated by the address latch enable signal. So this signal, the address latch enable signal, goes high during the T1 clock pulse and it remains high during the entire T1 clock pulse. This signal indicates that there is a valid address that is available on the address lines. Okay, and during the negative edge of the address latch enable signal, the valid address, the complete valid address of the location from which the data has to be fetched or the data has to be read will be available on the local bus. Okay, so as we know, the 8086 has a 20-bit address. So this address lines are split across the address bar status lines and the address bar data lines. So during the T1 clock cycle, the address bar status lines will have the higher order address lines, that is from A19 to A16, will be available during the T1 clock cycle, and also the lower order address bits, that is from A15 to A0, will be available on the address bar data lines. Along with the address bus status lines, the BHE signal, that is the bus high enable signal, will also be active, which indicates that the data will be available on the higher order data bytes. The address bus status line will indicate the status values, that is from S7 to S3 during the after the T1 clock cycle. The status lines will be available on this address bus status lines. And in the address bar data line, from this T2 clock cycle, it will be used for data, that is the time multiplex address bar data line will be used for receiving the data during the after the T1 clock cycle and during the remaining clock cycles. The bus after the T2 clock cycle, this valid address, that is the complete 20-bit address, will be removed from the local bus and it will be sent to the output, and the bus will be tri-stated, that it is neither will be in a 0 or 1 state. Then the read signal, the RD bar signal, is also activated during the T2 cycle, which indicates that it is a read operation that has to be performed. Now this RD bar signal, it causes the address device, that is the device from which the read has to happen, to enable its data bus drivers. So whenever this RD bar signal goes low, the valid data will be available on the data bus, and this is indicated by the DEN bar signal or the data enable signal, which is also an active low signal, and it goes low indicating that there is valid data that is available on the data bus. Okay, and the address device will drive the ready line high, that is it indicates that it is ready for the data transfer to happen. And whenever the processor returns a read signal to a high level, the address device will again tri-state its bus drivers. And during the entire duration of the read cycle, that is from T1 to T4, the DT R bar signal, that is the data transmit receive signal, will be low, which indicates that it is a read operation that is being performed during the entire clock cycle. Now let's look into the write cycle timing diagram for the minimum mode operation of 8086. Like in the case of read cycle, the write cycle is also having 4 clock states from T1, T2, T3 to T4 and the intermediate wait state of TW. Now this intermediate TW wait state is used in case if the devices are slow and then it needs to wait before the operation, whether the write or read operation has to complete. So it is more or less like an idle cycle which is used. So in case if the device needs to wait before the operation has to be completed. Okay, like in the case of the read cycle, the write cycle also begins when the address latch enable signal is asserted. That is, the address latch enable signal will indicate that there is a valid address that is available on the address bus for an read or write operation to happen. In this case, it is a write operation. And the memory bar IO signal, that is the MIO bar signal, that is also used to assert whether it is a memory operation or a IO operation that has to happen. Alright. So when the address latch enable signal is becoming high, it will indicate that there is a valid address that is available. This valid address will be available on the 20-bit address lines, which comprises of the A19 to A16, that is address bus status lines. The higher order bits will be available on the A19 to A16 address lines, and the lower order bits of the address will be available on the A15 to A0 lines. So during the T1 clock cycle, during the T1 clock pulse, the complete address will be available on the address lines. So after the T1 clock pulse, during the T2 clock pulse, the processor, the address is now available, the address to which the write has to be performed, the write has to be performed onto which location, that is now available. So after the T1 clock pulse, during the T2 clock pulse, the processor will then send the data that is to be written to this particular address location onto the data bus. And this data remains on the data bus until the middle of the T4 state. Okay. And here in the case of the write cycle, the write signal, that is the WR bar signal, it becomes active at the beginning of T2 itself. Unlike in the case of read cycle, the RD bar signal, it is somewhat delayed, and it will not become active during the at the starting of the T2 signal itself. But in the case of the write cycle, the write signal becomes active from the very beginning of T2 itself. Now, the write signal is an active low signal, and it will become active low at the beginning of T2. And at this time itself, the data enabled signal, that is the DEN bar signal, also becomes low, which indicates that there is a valid data available on the data bus. And during the entire duration of the write cycle, that is from T1 to T4, the DTR bar signal, that is the data transmit bar receive signal, will be an active high, which indicates that it is a data transmit operation, which is a data transmit operation, that is a write operation that is being performed currently. The MIO bar signal, the RD bar signal, and the WR signal together will indicate what type of data transfer operation is being performed. As given in the table, if the MIO bar signal is having a value of 0, the RD bar is also having a value of 0, and the WR bar signal is having a value of 1, then it indicates that it's an IO read operation that is being performed. Because the MIO bar signal is low, that indicates that's an IO operation. Here the RD bar is also low, which indicates the read is being performed, and the WR is high, which indicates that there is no write operation being performed. So together it will indicate that it's an IO read operation. Similarly, when the values are 0, 1 and 0 respectively, it indicates that's an IO write operation that is being performed. If the MIO bar signal is 1, that means it's a memory operation, and if the RD bar is 0, that means it's a read operation, and the WR bar is 1, means there is no write operation. So together it will indicate that is a value of 101 will indicate that it's a memory read operation. And in the same way, if the values are 1, 1 and 0 respectively, then it indicates that it's a memory write operation that is being performed. Now let's look at the hold response sequence of the minimum mode operation of 8086. So the hold pin or the hold signal is being checked by the processor at the leading edge of each clock pulse. So from the figure, if you check the figure, we can see that the hold pin or the hold signal is being found active high only during the leading edge of the third clock pulse. So it is at this time only, at the leading edge of the third clock pulse only, the hold signal is being found high. So what happens here is that if it is being received high, or it is being received active by the processor before the T4 of the previous clock cycle or during the T1 of the present clock cycle, then what the processor does is that the processor will activate the HLDA signal or the hold acknowledged signal in the next clock cycle and for the succeeding bus cycles. And it will also give the control of the bus to another requesting bus master. Okay. So the HLDA signal, as we can see, that it will become active during the very next clock cycle, that is during the fourth clock pulse, it will become active. Okay. Now the control of the bus will be taken back by the processor. It will not be taken back by the processor until the requesting master drops the hold pin to a low value. So we can see that as soon as the hold pin becomes a low value, the processor, what it does is that it will drop the HLDA signal to a low value at the trailing edge of the next clock. When the hold pin goes low, the HLDA signal also goes low during the trailing edge of the very next clock cycle. So this is how the hold response sequence happens in the minimum mode of 8086. The maximum mode configuration of 8086. The 8086 microprocessor operates in its maximum mode by strapping its MNMX bar pin to ground. That is, when it is a 0 value for the MNMX bar pin, then the 8086 will be working in its maximum mode configuration. In the maximum mode configuration, the processor derives the status signals S2 bar, S1 bar and S0 bar. There is a bus controller chip, which is a separate chip that derives the control signals from these status signals. From the status signals S2 bar, S1 bar and S0 bar, the control signals are being derived by the bus controller. Now, as the name suggests, in the maximum mode, there may be more than one microprocessor in the system configuration. The components in the system in the maximum mode of 8086 is same as that in the minimum mode. Now, The basic function of the bus controller chip IC8288, as we said before, is to derive the control signals, to derive the various control signals. The various control signals are the RD bar and WR bar, that is the read and write signals for memory read, memory write, and IO write and IO read. And also it has the other control signals such as the data enable signal, that is the DEN bar signal, the data transmit receive signal, that is the DTR bar signal, the ALE signal, that is the address latch enable signal. Now, the input lines that are there for, or the input signals that are there for this chip 8288 are the input lines, the status lines S2 bar, S1 bar and S0 bar along with the clock pulse. These inputs to the bus controller chip are driven by the CPU. Now, when these input lines are given to the 8288 chip, it derives the output control lines, which are, as said before, the ALE, DEN bar, DTR bar, and the read and write signals for the memory and IO read respectively. The AN bar signal, the IOB signal, and the CN signal are specially useful for multiprocessor systems. The AN bar and IOB signals are usually grounded, and the CN pin is usually tied to a plus 5 volt supply. Now, coming to the IO read command and IO write command signals, we have the IO RC bar and the IO WC bar signal, which indicate an IO read operation and an IO write operation respectively. These signals enable an IO interface or an IO device to read or write data from or to the address port. Next, we have the memory read command and the memory write commands. These are denoted by the MRDC bar and MWTC bar, which indicates a memory read command and a memory write command respectively. Both these commands instruct the memory to accept or send data from or to the bus. For both the write command signals, that is for both the memory write command signal and the IO write command signal, there are advanced signals that are available. These advanced signals are named as AIOWC bar and AMWTC bar, which indicates advanced input output write command and advanced memory write command respectively. They serve the same purpose as that of the IOWC bar and MWTC bar, but they are activated one clock cycle earlier than these signals. Now let's look at the comparison between the 8086 and the 8088 microprocessors. The instruction queue or the code prefetch queue in 8086 is 6 byte long, but in the case of 8088 it is only 4 byte long. The 8086 has a 16-bit wide data bus, whereas 8088 has a 8-bit wide data bus. The bus interface unit will fetch a byte from the memory to load the queue only if there is at least 2 bytes available in the case of 8086, whereas in the case of 8088, the bus interface unit will fetch a byte from the memory to load the queue if there is at least 1 byte that is available free. The 8086 has a BHE bar signal or a bus high enable signal on pin number 34. The 8088 does not have a BHE signal or the bus high enable signal. The 8086 does not have the SS0 signal, the SS0 bar signal, but in the case of 8088 there is an SS0 bar signal, but it does not have the S7 pin. The control pin in the case of 8086 is the MIO bar signal, whereas in the case of 8088 it is the IO M bar signal. That is, in the case of 8088, the memory operation, if it has to indicate a memory operation, then the IO M bar signal has to be active low. And if it is to indicate an IO operation, then the IO M bar signal will be active high, whereas it is the other way around in the case of 8086. The 8086 takes less time for execution, but 8088 takes more time for execution as it requires 4 additional clock cycles. That's all in this session. Thank you everyone.